All right. Welcome, everybody, to this month's edition of Pizza and Programming. This month, we have Brenton Kenkel from the Department of Political Science, who's going to walk us through an R demonstration. So I assume if you're here, you have some level of interest with using R or some level of experience using R. Can people kind of just show of hands, kind of shout out, what are some of the most painful parts about using R on the cluster? What do you like? What do you not like? What's that? It's faster?
I don't like that it has to store data in a RAM. That's what I don't like.
Okay, it has to store everything in RAM. Okay, what else? Is package management easy? Like managing all of the R packages on ACCRE? Or is that sometimes painful? All right, no response. Well, I was hoping that the answer would be yes, to segue into this next piece where we'll have a deeper dive into this tool called LMOD at next month's edition of Pizza and Programming. But just to provide a teaser of sorts, we have a tool that if folks are accustomed to accessing other supercomputing environments, you might be more accustomed to using a tool called Module rather than set packages and package info. So we're using a version of Module called LMOD, which makes package management a lot easier. Okay, and so Module avail is the equivalent of typing pkg info, so it shows you everything that's installed. The difference with LMOD, though, is that it's more intelligent about dependencies. So it understands that, okay, I can't load this piece of software because it depends on another piece of software that first needs to be loaded. And so at the bottom of that chain is generally something called a compiler. So in this case, I'm going to load module load GCC, and tab autocomplete is enabled, which is really nice. I'm going to load a particular version of GCC. And now if I type module avail a second time, you'll notice that new packages are now accessible and available. All right, so there's this additional section at the top that says applications built with this particular compiler. All right, so you would have to know this, and there's a way to search for this information that we'll talk about in next month's seminar. But for now, just suffice it to say that I also need to have a version of MPI in my environment in order to load R, because there are some MPI R packages that are enabled on the cluster, so R technically depends on those. So if I want to load those, I can do, in this case, a module load open MPI / tab, and that will load a version of MPI 1.10.3. And now if I type module avail, we have another section available. And so the top section now is applications built with GCC OpenMPI. All right, so now this is where we see things like Python, R, which we'll talk about today, and an assortment of other tools that you may or may not care about. So since today is all about R, let's go ahead and load R version 3.2.3. Question, yeah?
Yes, that's only going to fall down if you try and run something with the MPI, isn't it?
Correct.
Yeah, so for general purposes, not using MPI, it's completely fine to just load R regularly. So I haven't had a problem with it ever before.
So, yeah, so in this case, you would actually have to go ahead and load MPI, even if you're not using the, is it called RMPI? Even if you're not using the RMPI package, you would need to go ahead and load.
The old system still will work, though, right?
It will for now, but once we upgrade our operating system to CentOS 7, PKG info and set packages are going to go away.
Okay, cool. What kind of time frame is we running?
So the upgrade is going to start in August, and we're aiming to have everything completely migrated over October 1st.
Okay, fantastic.
Good questions. All right, so now I have R loaded, and I can convince myself of that if I type which R. Let me make this a little bigger. If I type which R, it points to a version that's installed at 3.2.3, and if I do an R -- version, it will come back with, yes, version 3.2.3, which is codenamed Wooden Christmas Tree, They always have cute names that they like to use. And if I want to load R, I just type R, and it's going to drop me into kind of an R session. And the really exciting thing here, I hope I get this command correct. Is it packaging? Is this? I don't think this is right. Is it installed?
It's installed dot packages.
Yeah, that's. I was counting on my R expertise up here to come in handy. So this will come back and tell me all of the packages that are already come installed within R. And the really nice thing about transitioning to the system is it bundles up a bunch of the really commonly used scientific computing packages. And so that gets cut off on the screen a little bit, which is unfortunate. And where's my mouse? I've lost my mouse. Well, at any rate, there are tools like RMPI, ggplot2, I think, is a really popular. I'm not an R programmer at all, so I don't pretend to understand what the important ones are. Snow. Anywho, you can peruse these to kind of take a peek at what will already be bundled up and available for you to use. So you get out of the business of having to install these packages yourself within your home directory and doing your own package management. So that was something I just wanted to lead off really quickly with, and we will take a much deeper dive in next month's Pizza and Programming Seminar. So with that, I'll go ahead and hand it off to Brenton. Let me get, assuming you want your GitHub, GitHub/ACCRE/R. Whoops. What did I miss there? There we go. So all of the material that Brenton will be covering today is available on GitHub. If you go to github/ACCRE/R and then parallel workshop, he's created a really nice README and such that I'm sure he'll walk through. And let me go ahead and close this out as well, just to prevent confusion. Is that big enough, or would it be helpful to make that a little larger? Larger? Okay, so with that, help me welcome Brenton.
Thanks, Will. So just before I get started, so who here has experience working with R? Okay, pretty much everybody. Okay, so I don't need to convince you then why R is a valuable tool for data analysis, because you already know, you already use it. This is good. It'll save us some time. So so what I want to talk about today is using R on in a cluster environment like ACCRE, and particularly how your R code can benefit from parallelization. Hence the title of the workshop, Parallel Processing in R. I assume also, is everybody here familiar with submitting jobs to ACCRE through the Slurm system? Most people are? Okay, I'm getting enough nods that I feel okay about that. So so I'll skip why R. So the basic advantage to parallelizing your R code or your data analysis code more generally is we have lots of processors available to us. If you're using ACCRE, then depending on your own fair share and bursting limits, you have dozens or hundreds of processors available to you at any given time. And even if you're just running R on your own laptop, odds are that if your laptop is at all a recent computer, it has a multi-core processor with maybe 4, 8, or 16 cores that you can use. And if you're only running your scripts on one processor at a time, then and you have computationally intensive data analysis projects, you're spending more time waiting for your results than you ideally would. And so if you can smartly split up the tasks that you have and distribute them across various processors, you can get results quicker, get papers published quicker, and be a happier, more balanced person. So in general, if you have a computationally intensive task and you have, say, n processors available to you, like 10, if you can dice it up in the right way, you can reduce your computation time to something like 1 over n of what it would be if you just ran it on a single processor, right? So if you have 10 processors, maybe 1/10. I mean, that's kind of a theoretical limit. In reality, it's not going to be quite that efficient, but there's lots of common data analysis tasks that you can do that are going to benefit from this sort of splitting up and parallelizing. And so in my own research, I'm a political scientist. I study international conflict. I'm sure you're all very eager to learn about programming from a political scientist. I do a lot of fairly computationally intensive work where a lot of times the data analysis involves doing some kind of structured repetitive task where the results of one piece of that task don't necessarily depend on the results of other parts. So for example, I use multiple imputation when I'm dealing with missing data in my data analyses. So make, say, 5 or 10 copies of the data and fill in the missing values randomly differently for each of those imputed copies of the data. And then I run the same analysis on all of my 5 or 10 imputed data sets, right? That's if the analysis is computationally intensive, that's a really good candidate to parallelize, right? That I don't need to run the first one and then the second one and then the third one. I can just find 10 processors, distribute the 10 jobs to the 10 different processors, and then collect them all together at the end and merge the results, right? Other things, other kinds of tasks that you might want to do in parallel. If you do machine learning, you might be using k-fold cross-validation, where again, you're slicing your data up into a bunch of different parts, training models on one part and making predictions for another part, right? That's the kind of task that, again, can be split up and distributed across processors. And in fact, if I'm able to get through everything today, which I hope I can, but we started late, we'll see an example of doing exactly that and how there are some nice built-in tools to speed up cross-validation by taking advantage of parallel computing. Another example that's common in data analysis is bootstrapping. If you're using bootstrap resample methods to make inferences, that's another thing where you can split your bootstrap resampling across many processors in order to cut down the amount of time that's being taken up by the computation, right? The amount of wall time, not the amount of CPU time. So basically any task that you have where you're performing the same kinds of computations repeatedly and those computations don't depend on each other's results is a good candidate to run in parallel, right? So now a key exception, the kind of computationally intensive data analysis that you can't really do in parallel would be something like Markov chain Monte Carlo, where if you're running MCMC, then iteration n, you're starting from the results of iteration n minus 1, right? And so because you have that interdependency between tasks, you can't distribute it. You can't distribute it in parallel across different processors, right? Now, if you're running like multiple chains or something like that, or each iteration is so computationally intensive that it itself might be a candidate to parallelize. Those are ways that maybe you could use parallelization with MCMC, but the basic Markov chain itself is not something that you're going to be running in parallel. So I'm going to focus today on more of what are called these like embarrassingly parallel tasks, where you're doing the same thing or a similar thing in a way that doesn't depend, where there's no interdependency between iterations in your results. So there are two basic ways that conceptually that you can parallelize your R code in a cluster environment like ACCRE. So, and I'm going to talk about both of these methods today. So one way to do it is to use what's called like a job array, right? Where you're going to actually run the same script many times, right? So if you have, say, 100 tasks, you're going to run the same script 100 times on slightly different inputs. Right? And this is this is conceptually a little bit maybe a little bit difficult, because it's, at least for me, it's not the way I'm used to running R code on my own machine, right? I usually figure if I have an analysis, I have my analysis script, I'm going to run it once, and I'm going to get the results at the end, right? Whereas this method that we'll go through first involves running, dozens or hundreds of different R sessions, each taking the same script with different inputs. So before I get ahead of myself, I'm going to talk about, I have some example data that I brought for show and tell today from the social sciences that I'm going to be using as a minimal example to show you the different ways you can write your R code in parallel. So just to be clear, I want to be upfront about this. So the data analysis that I'm going to be showing you today is something that you could run in about 1 second on your laptop in a for loop. Because I wanted, honestly, when I was testing the code, I didn't want to wait forever on ACCRE or use up my valuable fair share. But I hope that the concepts that we're going to talk about will port over to the more complex analyses, where in terms of computation time, you'd actually want to parallelize. So if you look on the GitHub page where this is, I have a CSV data file called wdidata.csv. WDI is the World Development Indicators dataset put together by the World Bank. It's one of the most commonly used datasets in political science and economics. Has all kinds of valuable statistics on economic and social life. And so the data file looks like this. We have countries, Afghanistan, Albania, and so on, for each year, 1990 through 2014. So we repeatedly observe each country. And then we have 3 variables in our data set. Female labor force participation, or female LFP. So what percentage of the country's female population above age 15 is in the workforce. Fertility, which is the number of births per woman in the country. And GDP per capita of the country. Right? And so what I'm interested in for today's purposes is the relationship between fertility and female labor force participation, holding fixed the country's GDP per capita, and how that changes over time. Right? So what I want to do, and this is an example of the kind of analysis that we would run in parallel, is I'm going to run a regression of female labor force participation on fertility and GDP per capita. I'm going to run one regression for 1990, another one for 1991, another one for 1992, and so on up through 2014. Right? Now, again, each of these regressions, because there's only like 200 countries, takes about 0.001 seconds on your computer, and you would never need to parallelize it. But if I were doing something fancy, if instead of running a linear regression with 3 variables, I was running, a random forest with 1,000 variables, then it might start to make sense to distribute this task over numerous computers. And so this is my data. Is everyone here familiar? Or I shouldn't say is everyone. Who here is familiar with running regression in R? Okay, most people are familiar with the R regression syntax. I will, in the interest of time, then I will not dwell on that. So if just on my own computer I wanted to run the 1990 regression here, I would load in my WDI data. I would run the linear model, subsetting to 1990, and then I could do things like look at my coefficients and calculate a confidence interval. Right? And so what I'm going to do now is show you the script I would use to distribute this using a job array over ACCRE. So what I'm gonna have here is a script called WDI by year.r. And what this is going to do when I run this script is it's going to take an argument from the command line, and it's going to use that argument to determine which year to run the regression for. Right? So if you call it at the command line with the argument 0, that's going to be 1990, 1 is 1991, and so on. And so what we're going to do then is run this script 25 times for each 0 through 24, right? Each of the 25 years that we have available to us. By the way, the reason that I do it in this kind of counterintuitive way, so you might wonder, why don't you just make the command line argument the year instead of starting at 0 with 1990? The reason is that the Slurm system doesn't like array numbers above 1,000, and so if you try to give Slurm an array that starts with 1990, it will get mad at you and not run your job. Or at least that has been my experience in the past using a very similar analysis. So
I don't think it's true anymore. But yeah,
well,
I think back in the day.
okay, back in the summer of 2015 when I was doing this. So hooray for that! Hooray for the changes to Slurm, of which I was unaware. I'm glad. So is there a cap now?
Yeah, but it's much larger. I think it's closer to like 30,000.
Okay, well then, yeah, you will see. You may soon see an updated version of these notes where I don't do this particular little hack. So you're going to call this script using something like the command. So R script wd by year .r 10 for the year 2000. And so the first thing I have in the script here then is I'm reading in the command, the arguments from the command line. I use the trailing equals true option so that I'm only pulling in stuff after the original R call, any arguments to the R call, and the name of the script itself, because I just care about this last, what we put trailing. So I'm gonna read in the arguments using the command args function. Now by default, R is gonna read in all of those arguments as strings, but we want this to be an integer. So I'm gonna take the first argument, convert it to an integer, and then do my now obsolete adding 1990 and store that as the year, right? And then I'm just gonna run. I'm gonna load in my data from World Development Indicators. I'm gonna run my regression, now subsetting to whatever my chosen year is. And then I'm gonna make a data frame to store my output that has the year that I ran the regression for, the coefficient on fertility in our female labor force participation regression, and the bounds of the 95% confidence interval around that coefficient. And then I'm gonna store it to this output file, wdi array results.csv, where each time I run the script, it's going to append a new line to this file containing the results of that regression. Right? Because, so again, if this were normal world and I was just running the R script on my own computer, I would just write a for loop, go through these 25 years and assemble a data frame containing all of them, and then spit out that data frame at the end. But what I'm doing when I use a job array is I'm splitting this up over 25 different machines, and each of them is going to separately run this script. And so they're each going to be separately writing out my results. So if you're calculating something more complicated than, say, a line or two of data, it can get tricky when you're using big job arrays, because you need to then store all of the different results of all of your different scripts, right? If you have an array of 1,000 things, and then you have to save 1,000 files to your scratch space on ACCRE, it can get a bit unwieldy to manage. Luckily here, I've picked a minimal example where I can just write a line to a CSV file. And so if I were to go into my parallel R workshop directory here, So I've already uploaded my WDI by year.r file. So if I were to just do this manually, say R script WDI by year 0 for 1990, it's going to run. It'll take a second. It's all done. And now you see I now have this WDI array results, which if I've done everything right, contains my, my 1990 coefficient estimate and confidence interval. So we see here in 1990, fertility appeared to have a significant negative relationship with women's labor force participation. So now what we can do, so if I were to run this again, for say year 1, that was faster, and now it's added another line to my CSV output file. So what we're going to want to do is instruct Slurm to automate this process for us, right? To go through every year from 0 to 24. So I'm gonna let's see. So, and to do that, we're gonna specify in our Slurm submission script that we want an array. And so here I've written up a pretty standard Slurm submission script. I'll focus your attention on 2 lines in particular. So first there's this line here that says array equals 0 to 24. That means I want to iterate from 0 through 24. And then notice here I set my output file as the WDI by year %a.out. And so it's going to create 25 output files numbered 0 through 24, each corresponding to one of the years that we're running for. I got the heads up on LMOD from Will before this, so I'm here using module load, GCC, OpenMPI, and R. I was too lazy to put in all the version numbers, so I put in a line to spit out what R version was being used. I have it print out some metadata about the job, and then finally I'm going to run R script on WDI by year.r on the corresponding array task ID. So 0, 1, and so on through 24. And so what this is going to in effect do is going to put 25 jobs into the Slurm queue for me, where those, depending on my bursting limits and on my fair share, they might get run all at once. They might get run one by one or anything in between. And I'll get notified when they're all finished. And so what I'm doing here then is, 25 times loading in my data, running the whole thing, and saving output. There are some advantages to doing it this way, but I think it makes for kind of messy code, right? At least relative to the way that we're used to operating as R programmers in the way we structure our analysis, or at least the way that I'm used to doing it. So before I move on to an alternative way that lets us have slightly cleaner code, are there any questions about what I've done or shown here so far? Yeah.
So R uses just one core. Like I noticed in your Slurm script, you had n tasks equals 1.
Mm-hmm.
Right? So you're just using one core.
Mm-hmm.
I confess I looked ahead a little bit, and I've done this in other languages.
Mm-hmm.
But it looks like you can combine both methods and do, like, say, n tasks equals 4 to take 4 CPUs on each of your jobs if you have some sort of other function that can parallelize that you want to use that within your program. Right?
Yes, yeah. So I've done a little bit of that, though not enough that I'm comfortable putting it like into the tutorial. But yes, like if you have a structured job that you're pulling in different inputs depending on the command line argument, and then you're doing something with like multi-core processing within each job. Yes, these are not. I've set it up as if these are these are exclusive approaches, but in fact they can be combined depending on the nature of your task.
But R by itself does not multi-thread anything, right? Like it doesn't.
I don't think so.
I don't think.
I don't think so. I mean, if you're using like a multi-threaded BLAS, maybe. But in terms of R itself, I don't think so. Other questions? Yeah.
So the array has to be numeric, right? So if I wanted to do something across, say, 50 different tissues with some expression data, I would have to assign tissue names to a number. Everything has to be.
Yes, at least as I mean, I'm clearly behind on my array knowledge. So
Yeah, if you go to our GitHub Slurm repo, there's an example called Java Array 2 that allows you to basically call the files anything you want. You just store them all in a subdirectory, and there's a single special command that will grab the appropriate file names and then allow you to pass it to the program.
anything else before we move on?
Have you ever had a problem with all these jobs writing the same file? I think I had a problem once where, like, I exclusively program. Then again, I'm talking about a different language. So, so my just background, my experience, I've done stuff like this with other languages. I haven't done it with R.
Yeah.
And I've run into this before, where if I've got 1,000 jobs or whatever, they're all writing the same file.
Yeah.
That you can start getting conflicts if they're trying to write, or you get gibberish if they start
Yeah.
writing at the same time because they're on top of each other.
Yeah. So to be honest, whenever I'm using this for my own research, I always just write to separate files and then have a separate script that brings them all together at the end.
I usually have a collector script at the end
Yeah.
that loops through all, collects the results.
Yep, that's yes. You will see many scripts called collect.r in my various projects. But of course, this is the thing: is that I don't like writing these scripts. They make it hard. They make it hard for my co-authors. It's cleaner if we can do everything all in one. Okay, so I'm gonna, in the interest of time, let's move on. So the other way. The other way that we can do this, or one other way to do this, is to use MPI or another similar environment for multi-core processing in order to basically translate the for loop that we would have wanted to write into something that we can distribute in parallel. And so R has a nice package called for each, which is basically a re-implementation of for loops that allows for parallel distribution of tasks. And for each works in conjunction with this package do MPI, which gives for each instructions for parallelizing over MPI. There are a few different do packages. So there's like do snow if you're using snow for your cluster management. There's do MC for just local multi-core processing on your own computer. I'm sure that there are other ones that I am forgetting, but we're going to look at do MPI today. Which you would need to install. I don't think doMC and for each are included in the new the fancy new R module. So you do have to install those, or at least that was my experience as of when I was throwing my laptop against the wall yesterday. What I've written here is just the for loop that we would want to write for the kind of task that I've talked about, running this regression 25 times. So we have our years, 1990 to 2014. We set up our output as a matrix, and then we loop over our years variable and store the output in our output matrix, all using this for loop. So this is and you'll notice here that this for loop, the ith iteration doesn't have anything to do with the I-1th, right? We're not invoking last time's results or anything. These tasks are independent of each other. And so what we do to make this something that we can run in parallel in a cluster environment like ACCRE is to rewrite our for loop as a for each loop using the for each package, and register a parallel backend for each using do MPI or one of the similar do packages. And so for each it's a lot like a for loop with two differences. So the first is that unlike a for loop, for each in R is a function. So it's going to have a return value. This is actually nice. I write a lot of code that I'm not even doing in parallel using for each, simply because you don't have to set up a container for your output in advance. What for each is going to do is each iteration of your loop, it's going to take your return value and save it, and then at the very end return a list containing containing the return value of each iteration. Right? So whereas here, when we wrote an explicit for loop, we had to set up storage in advance. You'll see that when we use for each, we don't have to do that. Now, that's a benefit, and as we know, every benefit has a cost. The cost is that there's, as I've iterated before, you can't have interdependencies between steps of a for each loop. Right? So if you're going to be running Markov chain Monte Carlo, you're not going to want to write a for each loop to do that. So what I've written, and it's also in the GitHub here, and I've pasted it into the README, is an R script that takes the for loop we would have wanted to write to do this task, rewrites it as a for each loop, and uses that to run the task in parallel using MPI. So this is a little bit more involved in some ways than the last one, because the first thing we're gonna do is set up our use of MPI on the cluster. So I have this section of the script called cluster setup, where we're going to load up the for each and do MPI packages. And when we load do MPI, that's going to load the RMPI package that Will mentioned before as one of its dependencies. To those of you who haven't used MPI on the cluster before, I want to emphasize what a favor the ACCRE folks have done us by having a version of R explicitly compiled against MPI and including RMPI, because it is kind of a pain to get MPI installed manually. So I very much appreciate the new module system. I've found before that sometimes if I have an error in the middle of a script I'm using that's parallelizing over MPI, it'll just sit there and not kill the job, which one time I used a whole lot of fair share on a job that was not doing anything, and I was not a happy camper. So after some Googling and Stack Overflowing, I found that inserting this line helps reduce the chance of that happening. I will not say eliminate the chance. And then there are these two more important lines here. So I'm gonna start an MPI cluster and assign it to the variable CL. If you're running R using srun through your Slurm submission script, it'll automatically detect how many nodes are available, and so you don't have to explicitly tell it in here. And then we have another command called register do MPI, which we run on our MPI cluster object, that's going to instruct for each to use the MPI cluster in order to perform parallel computations. So then here we have loading up the data as before. So this is the data analysis phase of our script. And then what I've done here is I've rewritten our for loop as a for each loop. So you'll see, since for each is a function, we're assigning it to a variable called output. And we're going to loop over years from 1990 to 2014. I have this argument here called .combine equals rbind, so that it's going to take each iteration and bind them together into a matrix instead of returning a list. It's just a convenience function to make our lives a little bit better. And then finally, we have this operator do par, which is a way to tell for each, do it in parallel. Right? And so when you use for each in combination with do par, what for each does is ask itself, is there a parallel backend registered? Which in this case there is, because we registered the MPI backend on the CL cluster object. And so when for each sees do par, it looks for a registered backend and is going to use that. As I mentioned before, there's numerous different do packages that allow you to use different backends. And so, for example, if you want to write a script that'll use multi-core processing on your local machine, but use MPI as a backend when you run it on ACCRE, you can do that with some conditional statements. So we wrote the for each loop that way. We're going to run our regression in here for each year, and then spit out the same output that we'd been spitting out in the other script. And then, so now, with just one script run, instead of 25 separate script runs, we have our output assembled all together. And so once you become comfortable with the for each syntax, this is a way to make your code a lot cleaner in that you're not running, you don't have to have collection scripts, you don't have to do anything on the back end because all of your output's going to be assembled into one place. And then finally, you have to close up the cluster and instruct MPI to quit. And then your Slurm submission script here is going to look more like a standard Slurm submission script. So here I'm requesting 6 nodes and just assigning one task to each node. And I'm just running R script wdi mpi.r, and I'm running that within srun, specifying PMI2 as the MPI processor. That's just following the standard ACCRE instructions for using MPI. And so now I just submit one job that asks for multiple processors. It's going to run the whole thing at once, and it's going to spit back a unified piece of output at me, which, depending on your purposes, may or may not be more convenient than the other way. So so I have like 2 minutes left. I will put up the pros and cons, but before talking about the pros and cons of each approach, I just want to mention that one reason, even if you prefer in writing your own code to always use job arrays, one reason it's really valuable to get familiar with the for each package and with registering backends for it is that a lot of our packages that are out there for data analysis depend on for each and use it to incorporate parallelization into their code. So for example, something I use a lot in my own research is the carrot package for machine learning. So this has all kinds of machine learning algorithms incorporated. It has a convenient backend for cross-validation and other things. And if I register a parallel backend to the for each package, and then just call my training functions in carrot with a parallel equals true argument, it's going to automatically look for a for each backend and use it in order to do my cross-validation or other tasks in parallel. And so this is a way, if you're working with packages like that have already become part of this ecosystem, this is a way to very cheaply, in terms of programming effort, parallelize your code. And so in what we didn't get to today, in the notes, I have a less trivial example that does exactly that shows a way you can benefit here.
You can take some time to go through it. I took a peek outside and it doesn't look like anyone's waiting.
Okay.
So.
Okay. Question first?
How much efficiency do you lose with using a for each package? So obviously there's some overhead distributing the articles and that kind of stuff. Do you lose, have you found that because I used a bit, you found that I lose a bit of efficiency. Maybe I get, instead of, when you're using 2 cores, instead of getting half the time, it's about 3/5 of the time.
That comports with my experience. So one thing I try to do is to so so there's some overhead just with the the data being passed back and forth between your main script that's running it and the nodes that are being called via MPI. And so I try to structure my code in such a way that what's being sent to each separate processor is fairly big, because I don't want like every second something to be finishing and passing a message back, right? I want it to take like 5 minutes and then take the extra second in order to pass data back and forth. So that's one way. I mean, I will also tell you whenever like speed is really key for me, I just use job arrays instead. Whenever I'm really trying to optimize on performance, like during the summer of 2015, I was like always up against my fair share limit. Basically, I was using job arrays so that no second was being wasted. You're going to waste a couple more seconds doing it this way, but you'll also you'll save some programmer effort. Other questions? So just to show you real quick, so this less trivial example. I'm using a different data here from the UCI machine learning repository on whether or not people make more or less than $50,000 a year and some demographic attributes. And what I want to do is use a k-nearest neighbors algorithm to predict whether or not you make $50,000 or more from some basic demographic characteristics. And I'm going to do that using the ACCRE package for machine learning, and I'm gonna choose the number of nearest neighbors k using tenfold cross validation. And so what I'm going to do is, so in the ACCRE package we use the train function in order to train a model like this. And what I'm going to do is I'm going to write a script where, again, I load in for each and do MPI. I put in my error handling thing just out of superstition. And I start up an MPI cluster and register it as my backend for each. And then I'm going to load up the ACCRE package, bring in my data, and then I'm going to model your income as a function of age, race, sex, education, and the number of hours worked per week. I'm going to use k-nearest neighbors, center and scale the data beforehand. By the way, if you're not familiar with the ACCRE package, it's great. It changed my life. I'm not kidding. Then we're going to do tenfold cross-validation. And here I have, just as a benchmark, I have allow parallel equals false. So I'm going to run it once sequentially, and then I'm going to run it again. I just copy pasted, except I changed to allow parallel equals true. So since we have people about to come in, rather than run it, I will just show you the results here. So so this is from when I ran it. So the sequential model comes first. It took, if you see, it took about 150 seconds, so 2.5 minutes. I distributed it over 5 processors, and then it took 46 seconds over the 5 processors. So definitely not the, like, I would have loved it to take 30 seconds, like to divide time by 5. Didn't quite get there, but did get a substantial shave down from 150 seconds to 46 seconds. So all this stuff is on the GitHub. Thanks so much for coming, and thanks, Will, for putting this together.
Great. Thanks a lot, Brett. Since we intermingled questions and there's folks waiting outside, I think we should probably just wrap up. But thanks, everyone, for coming.
So when is the